very much, Tracy, for introducing me. As you said, yeah, Leeds graduate. I've been here now 2 years. I started with this project engineer role, which was it was all over the company. I would sort of drop into emergency teams going to help set up our test site, which we were doing back then. Or suddenly I had to work on grants for a couple of months. It was great. It was like a really sudden looks into all different aspects of the company, which was really, really good, like broad look at everything that Skyrora does and a lot of company-wide experience. But then during that time, I got to work a bit on the engine, and I was like, this is the stuff that I love doing, that I want to know more about. So that's where I got put into. And I've been doing that for a year now, apart from a small mission blip where I had to go out to Iceland for 6 weeks. Aside from that, it's been a year in propulsion, learning under some great experienced people, and mainly working in manufacturing and assembly. So trying to improve processes, speed up processes, cheapen processes. It's really, it's a great job. So Skyrora, this is our general approach. The new space enterprise that manufactures dedicated satellite launch vehicles to make space more accessible, greener, and cheaper. So we're not only a launch vehicle, which is sort of the thing that everybody knows about, but we try to do a couple of things on the side to broaden our audience. So we have the in-orbit services, which is maybe deorbiting old satellites, or sort of refueling satellites. There's many options that you can do once you move into like in-orbit servicing. So part of our USP is this mobile and modular launch complex, which means that we can go to anywhere really throughout the UK or Europe or the world realistically, that has a nice like 50 square meters of concrete. We can set up a few shipping containers and we can launch our vehicle from there. Which is a really handy thing, especially at the moment with a small launcher, having that versatility of last minute, we've got a license, we've got a payload, let's launch. Additionally, we've got this EcoScene, which is our proprietary green fuel made out of recycled plastics. That combined with the HTP that we use makes this big reduction in CO2 emissions. And obviously launching rockets is never going to be the cleanest the cleanest industry, but we are trying to make it as clean as possible, especially with manufacturing processes like 3D printing. Just the use of 3D printing means that you don't have like cut off metal that gets scrapped, or you can really design your parts as to optimize them as best as possible. And then also we use external and internal 3D printing companies. So we've developed our own in-house 3D printing technology, which is one of the largest 3D printers in the world, which is used to print large portions of our vehicle. So our approach to developing a rocket in a country that has not that much rocket experience is a de-risk approach. So we started off with Skylark Nano and Skylark Micro, which these are almost commercially available vehicles. They had our own like tweaks and stuff to them, but this allowed us to sort of get to know the process of building, assembling, testing, and launching rockets. So we took these, some we did in Scotland, some we did in Iceland, and not only does it help you build these processes of, I want to launch a rocket, who can be where and when. There's a lot of process management that you need to go through to understand really what's going on in a launch and to get people in the right place. And there's a lot of organization that needs to go into it. Not only is there that, but the government and licensing side that was a really good foot in the door. So we could be speaking to the Icelandic government or the UK government saying, we want to launch this thing to X thousand feet. What do we need to do? And so they might be like, oh, well, if it's only this much, go for it. Or they were like, oh, well, actually, you're going to have to fill out this and this. And it gets on some good speaking terms with the CAA or the Icelandic Space Agency. And both the UK and Iceland are places that haven't really launched rockets from before or of any considerable size. So it's a really good way to be working together with the governments and be talking about what process we're going to be needing for as we scale up these rockets. So then moving on to Skylark L, this was a good way to start testing lots of our subsystems. Ever since, so obviously you don't want to put all these systems that you've tested individually onto one huge expensive rocket and then be very nervous about anything going wrong. If you can do it on a smaller, cheaper version, you get to test these things more often, which is just essential. I don't know if you know the TRL system, which means technology readiness level. Essentially, you just have to, so you starting out from design through qualification, you have a sort of rank, and the highest rank is 9, and you can only achieve 9 by actually having something that it has to have, I think it's worked in the environment basically. So you can only do that by flying it. So by using similar systems on XL that we do on L, we can actually have TRL level 9 systems used on the first XL flight. So this is Skyrora XL itself. It's about 23 meters tall. It's got 3 stages, which is fairly uncommon for rockets, but it varies. It's all HTP and kerosene and ecosene fueled, and we try and push towards these 4 USPs, as you can see on the side. So quick and simplified access to space. The great thing about using HTP is that it's non-cryogenic. So on traditional vehicles, quite often using the cryogenics, you'll fuel up the vehicle, get ready to launch, and if there's anything that makes you hold, the oxygen, usually liquid oxygen in the vehicle, starts boiling off, and then you have to top it up and top it up and top it up as it boils off and just evaporates out and you lose it. HTP and kerosene, if they're at room temperature, you can just fill it up and you can just leave it there until it's ready to launch. So that, especially as we're planning to launch from Scotland, which does not have the most reliable weather, is a very useful advantage to have, where we can be ready to launch, hold for an indefinite period of time, and then launch when the conditions are favorable. Again, as I mentioned earlier, another USP is the eco-friendly launch, the HTP, the kerosene, the ecosene as well, very environmentally friendly approach to our design and flight. Another USP, the low G loading. This is more for the benefit of the customer. So as the customers will be satellite manufacturers, not necessarily huge companies, they want to reduce the amount of testing that they have to do on the vehicle, on their satellites. So instead of, I've heard stories of like astronauts on the Falcon 9, they say that second stage flight is a fairly bumpy ride when you're up there that close to the engine. So ours is designed to absorb as many vibrations as possible and have as low G loading as possible. So this means the satellites companies don't need to develop such sort of robust satellites that can withstand this. They don't have to withstand such extreme conditions during launch. And lastly, the in-orbit maneuvering. We like to compare it between SpaceX rideshare, which is one of our competitors. Obviously, it's a big competitor, and their rideshare is very cheap. But we consider that similar to getting a bus, where you're all getting on one payload adapter that's flying you up to orbit, and you have to wait an indefinite amount of time until that bus comes, because they only do them once or twice a year, and you're not guaranteed a space on it. And then when it does go up, you're dropped off in that orbit. You don't have much choice on where you're going. So we're much more of a taxi service where due to our quick and simplified access to space, you can then have it. We aim for between 8 to 12 months that you can from getting the contract to launching, and from there you can then you'll be put directly into the orbit that you're looking for, which is a problem that lots of satellite manufacturers are facing at the moment with the current rideshare model. So this is our space tug, which is the third stage, which is what will enable that the sort of very precise orbit locating. We plan to adapt, well, we are adapting it, so not only will it drop off a satellite in its own dedicated orbit, but it will then have enough fuel and propellant to then move into another orbit or a similar orbit, and maybe deorbit or refuel another satellite, because currently there's a growing issue of space debris, which I think maybe 2 or 3 days ago, the FAA gave their first fine for a satellite company that didn't properly, didn't have a sufficient end of life plan for their satellite. So this is a really important part of the market. Space is, while it might be huge, there is a finite amount of LEO and GEO orbits that we can use, and it's really important that we are responsible in going up there, helping out, as I say, deorbiting or refueling satellites that might need it. So this is just going on to a couple of Skyrora's recent milestones. This was the second stage static fire. So as you can see, that big yellow frame, I did a lot of the work on the integration of that with the second stage, which was a lot harder than you would expect. Somehow it took weeks, but we got it there. So this, it's the whole second stage of the vehicle. We took it out to Machrihanish Airbase. We had it on the back of a lorry. We had all 5 of these containers on the back of the lorry. I thought quite a smart trick was that all the equipment that we needed, we packed into the containers, shipped them all out, and then stacked the containers to make the stand. Well, we emptied them, then stacked them to make the stand, which was a nifty little trick and saved transport costs and stuff like that. Anyway, it fired as if it were in its like part of flight, just being dropped off by the first stage. It fires and then it would drop off the second stage. Normally, a second stage engine would have a much bigger vacuum adapted nozzle because you're expanding the flow into the vacuum of space rather than the higher pressure of the lower atmosphere. But because we can't test it in space, we test it at ground level. We have just a normal nozzle on it, in case anyone was wondering about that. And then this was, as I mentioned, I went on this mission last year, the SLK Launch, which was a huge effort by the team. This rocket had actually been ready for at least a year, I think it was, but we were waiting on permission from the Icelandic government and UK Space Agency, not Icelandic Space Agency. So when we did get it, there was a sort of, we had to make decisions. Do we launch it now as it's getting later in the weather window? Or do we wait until next year? And we decided we definitely had time. We had the team. Everyone's skilled enough to do this. So we went out there, had this huge company push, worked these long shifts in gradually worsening weather out in Iceland. In the far Iceland, I hear all these lovely stories about it being this beautiful, amazing country. We were in the far northeast of Iceland, where it is still beautiful, but when you're just concentrating just in a rocket, you could be in a field in Lanarkshire, or you could be in a field in Iceland, as it happened. It was all the same, really. I mentioned earlier, our plan is that you give us a square, 50-meter square concrete pad, and we can ship out there and launch from it. We didn't even get that out in Iceland. We just got a field that actually had a fairly severe slope. So the mud just got everywhere, and it was fairly grueling experience, but the team was incredible. We pushed so hard. We did just an enormous amount of work, and that was one of my best experiences at that company. The sort of 5 weeks leading up to the launch was just incredible. Unfortunately, as you'll see, I've got a small video later. The launch did not go to plan due to a software issue, which, despite us pushing that hard, it was something that had been set in motion years back. So it wasn't even the fact that we were pushing that caused that. It was just it was something that we could only really test in a flight situation, unfortunately, and it didn't go to plan, unfortunately. Anyway, on the day, I think it was similar conditions to this thick mist. You couldn't really see much, and then we were, I think I was about 9 kilometers away. I was working on range in the morning to essentially stopping any locals from getting too close, or farmers or stuff like that, and keeping people at bay. Not that it's that inhabited in the far northeast of Iceland. But yeah, and this sort of cloud, I was like, oh, great, well, we're going to launch this rocket and I'm not going to see anything. And then the cloud above it just moved, and I was like, well, this is turning out all right. And then a rainbow appeared above it, and I was like, wow, this is really turning out pretty amazing. And then there was nothing, which was a real shame. The vehicle managed to get up to half a kilometer, I think it was. I'm actually not sure about that. And then ended up crashing down back to Earth, which was a right shame. But here's a short video that shows some of the Iceland mission, and you can really see the conditions of that field and how little equipment actually we can take out there and launch a rocket that will go to 120 kilometers. So yeah, as you see, it sort of just veered off quite swiftly after launch, which was a real shame. But to see, we proved a huge number of systems actually, and improved a large number of processes from that. So it was an incredible learning experience for the company, and we have definitely progressed very rapidly since that, from being able to learn from the lessons that and experiences from out there. So this is just a brief talk about some of the stuff that we develop in-house. As Tracy mentioned, people don't often know quite how much the UK can do in space. And this list on the right, that's just some of the things that we do all just here in Cumbernauld. We have some more R&D that we have out in Dnipro, and we have another branch in Edinburgh and just outside of Edinburgh. So there's a huge amount of work. We can make composite high pressure tanks. We can make aluminium high pressure tanks. We do all of our own avionics and harnesses. The harness is sort of the wiring system for the engines. All that is done in house. There's like an incredible broad range of expertise just in this building, and yeah, it's for example, the propulsion systems and subsystems. We now have three engines that are all like either qualified or in the process of being qualified, and these have all been developed by us and tested by us. I did also mention this, our own 3D printer. This is one of the largest 3D printers in the world, actually. It's got this huge print bed. It's DED, which is Directed Energy Deposition, I think it stands for. Essentially, it's a laser. I think maybe 2 streams of powder and a laser that will combine and sort of fuse the metal into the same place. But ours is a hybrid 3D printer, so we can print certain amounts and then come in and machine it, and then print more and then machine more, or we can just print it all and then machine it at the end. But it gives this flexibility to the parts that we design and make, because quite often that's a problem with 3D printing is you'll print a part and then suddenly you've got to machine a face down at the bottom of it, and there's actually no way to get a bit a machine bit that's what, I don't know, 30 centimeters long that can reach down there. So it gives us a lot of flexibility, as I said. As a propulsion man, I'm just going to move on to the bits that I like talking about, which is the end. I mean, I like talking about a little bit, but the engine, which is the stuff that I love talking about. So this is our 70 kilonewton engine. This is currently in qualification and has been in the works for a few years. It's staged combustion. So this means instead of just pushing all the propellants into the combustion chamber and burning it, we push a little bit into, I don't know if you can see my mouse, but into this gas generator, which is, so it's staged because you burn a little bit here and then you burn a little bit more, well, you burn the rest of it here. So it comes in 2 stages. So hydrogen peroxide burns in here, which then powers a turbine, which then powers the pumps, which then pressurizes the gas. So the pressurizes the propellants. This means you don't have to carry these like huge high pressure tanks up to space. You just have normal tanks that hold low pressure liquid. You then use these very, very powerful turbo pumps to spin everything up to 200 bar and then force it into the combustion chamber, at which point when it combusts, you get very high speed particles out the back that give you a lot of thrust. So we have a regeneratively cooled combustion chamber and nozzle. So inside you're getting temperatures 2,000 to 3,000 degrees and any normal metal will melt at this. So you have to run these cooling channels down the side of, like, there's tiny little channels all the way down the side of this, all the way down and then back up. So you put all your propellant through that first, so it's coating the entire chamber, and then it comes back up and then it goes into the combustion chamber. And this means that it wicks away the heat from the wall and allows you to operate at those like extreme temperatures. Another issue that other engines quite often encounter is combustion efficiency. You have to have very like complicated injectors and stuff as you spray the propellant into the combustion chamber to ignite. You want to get full atomization, so everything's as small as possible and they're all as mixed as possible. Because ours is partially decomposed, we have loads of very hot gas in the combustion chamber. So as this mixes with the kerosene, it's a gas, so it mixes far better basically than a liquid-liquid interaction. As I mentioned, we built this test stand out near Edinburgh, which is used. So this engine's it can produce 7 tons of thrust. You strap it down on some combustion. Here's a picture here. Yeah, you strap it down just above these guys' heads up here. It then fires down here, and it's got you need these containers to hold it down while it's producing 7 tons upwards. And yeah, as I said, approximately 80% 3D printed. We use various 3D printing methods, some in-house, some out of house. But the 3D printing enables you to rapidly iterate designs. You can think of an idea and be like, oh, that will probably work, and then you can just go and print it and it's ready in a few days' time, whereas traditional methods quite often are much more laborious and expensive. And also, well, another classic example of 3D printing is these sort of complex geometries that you can get on parts that normal machining and traditional methods just can't recreate. And lastly, just hydrogen peroxide, which is our main fuel. It's the oxidizer, so the actual fuel is kerosene, but the hydrogen peroxide does the oxidation work. Some of the earliest rockets ever built actually use hydrogen peroxide, so it's got a huge amount of data and knowledge behind it, which we can tap into. And one of the key things is starting and stopping the engine. Well, starting the engine. When you, surprisingly enough, you'd think, oh, start a rocket engine. You just obviously everything's high pressure and it's all going to be hot. It'll catch fire. Not actually the case. Quite often there's many different ways to restart a rocket engine, and they're all fairly complex. Hydrogen peroxide, when it hits a catalyst, which can be any organic matter like copper or silver, will decompose into 600 degree steam. That steam is then well, 600 degree steam is hot enough to ignite kerosene. So when those two touch, you get ignition. There's no like, oh, will it ignite? Will it work? We don't know. It will work. It always works. So that's a really handy thing to have on our engines. Again, there's no turbine spin up. So quite often to start up your pumps, you have a turbine that's powered by, pumps that are powered by a turbine. To get that turbine spinning, to like start the whole process, to start dragging propellant through the system to then power the turbine. Normally you need like extra gas, or like you might use nitrogen or helium to spin it, that then like starts the whole process. Again, you don't need that with HTP. You just put it over a catalyst, it expands and it pushes the turbine. It does it itself. It's a really useful fuel. It's great. It avoids the gas generators on rocket engines are notoriously tricky. They require like very specific balancing and like self-regulation as you sort of throttle the engine. So this one, it's just, do we need more HTP? Yes, open a valve a bit more, and it just works. It's almost that simple. It's not quite that simple. It is rocket science, but it's almost that simple. And as I said, it's storable and non-toxic. Storable meaning we can leave it in an IBC in a field for 6 months, actually in a secure place for 6 months. And then when it comes to testing or launch, we can bring it out and it's ready to use. And if we are trying to launch, we can leave it on the pad for, 6 months is probably the longest period of time we'd want to do that. And anyone would want their payload sitting on a rocket for 6 months. But that's probably the longest we could do. But we could theoretically do that and still just press the button and launch it. So that's about all I've got about Skyrora engines and hydrogen peroxide. Thank you very much for listening. And if you have any questions, I thought I had a question slide, but oh wait, no, actually, sorry. I have one more video.